morning, everyone. Is this working? Yes. Yes. Welcome. It's my pleasure to introduce today's plenary speaker, Ferruh Özbudak, who is going to tell us about covering radius of some codes and related results. Please.
It works, right? Okay. Thank you very much. First of all, I would like to thank all the organizers for this excellent conference and giving me this opportunity to be here. This is my second time in Brazil. It was about more than 10 years ago. I visited Arnaldo Garcia in IMPA in beautiful Rio de Janeiro, and also I have seen beautiful town Parachi. I hope to visit more in the future. Okay. So this talk is a summary of my recent results, studies. I have learned a lot with collaboration from people like Thor Helleset and Patrick Solle. Actually, we all know we have to be lucky. Life is not easy. So I was very lucky throughout my life in mathematics. I first met Stepanov, then Henning Schlichtenau, then Niederreiter, then I met a lot of people. I learned a little bit from, this is because of my less capacity. I tried to learn as much as from them. And I have learned a lot from Patrick and Thor in the recent years. Okay, so I will start with very basics. So in this talk, we consider the constants is a field. So we work over a field, and our ambient space is an affine space, n-dimensional vector space over Fq. And actually, this kind of questions can be asked and have been studied and being studied as well for various related domains and structures. But in this talk, I will stick to finite fields, linear codes over finite fields, and only with Hamming metric. And the Hamming metric, I just remind, in the ambient space, in order to do some combinatorics or discrete geometry, you have to introduce a metric satisfying triangle inequality, and it is the Hamming metric which counts the number of distinct entries if you choose two vectors in the ambient space. And since the ambient space in this case is additive, one can also define the weight for each vector, which counts the number of non-zeros, and actually defining the Hamming distance is equivalent to defining this weight. And of course, if the code is nonlinear, weight is enough to find the minimum distance. So I didn't define the minimum distance for a code, so our code will always be a linear subspace in the ambient space Fq to the n, and it will be Fq linear always. And so if the dimension is k, so you have q to the k elements, and you list all q to the k, choose two distinct code words, and you put all of them, and you can find the distance between all of them, and you can try to find the minimum. It is a very expensive operation, but once you can do it, then assume you know the minimum distance d, then one can define the error correcting capability or the packing radius of the code as d minus 1/2. So these, but there is another combinatorial and very natural notion. What you do is somehow the opposite. So, like in calculus, we also have balls in the Hamming space. So for these Hamming balls, we take a center and we consider in shells all the all the words in the ambient space, and this up to radius r, and r is a non-negative integer. If r is 0, you just take the code word at the center. Then you choose all the code words in the ambient space, and you try to draw the balls around the code words of the same radius. And you start with 0. Once you do 0, you have a bunch of points. Once you put ones, you have small spheres, and you increase, and obviously everything is finite. At a point, you cover everything, and you stop exactly at the point you cover everything, and this point is called the covering radius. It is the definition of covering radius. Sorry? Yeah, it is typo. Sorry, I will use Q0 in the others. Sorry. So you can consider it Q. Okay, so it is well known, and if you think a little bit, it is easy to conclude that this packing radius is always upper bounded with the covering radius, which we will denote usually by R of C. And then, like in many other objects in our studies, one would be interested in the case when this inequality is tight, and it is called perfect. And in the next slide, I will show that. So I have seen many success stories of coding theory, and one of the important success stories is classification of all linear perfect codes in 1970s. And actually, there is no room to study linear perfect codes anymore. So, but there is a lot of room to study quasi-perfect codes, and some of our results give some contributions for this, and quasi-perfect means we have one defect. So I have to present this result. Actually, it is from the important book of Hofmann and Pless, and if you go to the relevant page, they say the following. I just quote: the classification of the perfect codes as summarized in this theorem was a significant and difficult piece of mathematics in which a number of authors contributed. I mean, it is probably dangerous for me to cite all of them since I may forget, but I mean, I can say some people like Lyot, Van Lint, Titavanian, and I am sure there are others. And so, but what is relevant for us is to say that actually this is a wonderful result, and I have seen also applications in algebraic geometry, real algebraic geometry, and many other things. So in order to understand this theorem a little bit, I have included some background. So the first item says Hamming codes. So actually this theorem says that if you want to construct perfect linear codes, you cannot do if the minimum distance is different than 3, 5, or 7. And actually, you cannot do anything new. Everything is done. And first, when the minimum distance is 3, they all come from the Hamming code. And the Hamming code is actually dual code of the simplex code. And the simplex code has still a lot of parameters, but the Hamming code has always a minimum distance 3, and you can define it using geometry. In some sense, you consider all one-dimensional vector subspace, distinct representatives of all one-dimensional FQ linear subspaces in FQ to the R, and you put them in columns, and this will be this will help you to define both simplex code and Hamming code. I will give a very basic example in the next slides, and this example will be a particular case of Hamming code when Q is 2 and R is 2. And the second is more involved, and I couldn't put the generator or parity check matrices for these codes you can find. And these are only, and more important also, we do not have for arbitrary finite fields, we have only for binary F2 and F3, the other codes, perfect codes. Okay, so another still two more slides for understanding the covering radius. So this is the maybe simplest example of a perfect code. So when you put Q is 2 and R is 2, you get a 3-1-3 code over F2, which is in a sense a repetition code. But if you write, so this you understand why it is repetition. There are only two code words, the origin and 111, and then what you do is probably this picture. So this is the ambient space F2 to the 3, and this center and this center, they form the code. So if you take the Hamming poles of radius 0, you get only this point, and you cannot cover obviously the whole space. If you take the Hamming pole of distance 1 from this center, you know, these are the words in the ambient space, exactly the 3 words which have distance 1, Hamming distance 1 to this code word. And if you do the same for 111, you obtain these words, and luckily none of them intersect. There is no intersection, and then we cover everything, and it is the perfect code. And in general, this is hopeless, and we have very little number of perfect codes. I mean, only this classification. So then, of course, one can try to consider the exact covering radius of a given code, and it is related to decoding problem. And to be honest, I didn't read detail these papers, but I believe they are correct, and they say this is a very difficult problem, NP-hard and co-NP-hard. And there is an excellent book and an excellent survey, and you can learn a lot if you read these results, and there are a lot of applications beyond decoding, actually. So now, in these 3 slides, I will give a easier for us, or at least for me, definition of covering radius using the parity check matrix without this combinatorial view. It is the following. So once you have a linear code of dimension k, I will not care that much about the minimum distance, but let us keep it for the time being. So then you can define the code using a parity check matrix, right? So the dimension of the code is k, length is n. So the parity check matrix traditionally is considered as an n minus k times n matrix, and the code is considered as the right kernel of this parity check matrix. So now what you do is the following. I find this very interesting. So, and this is something I learned from one of the papers of Thor Helaset in 1970s. Once you write the parity check matrix, these are the columns. So you have n columns. And first, you may observe that, so this has rank n minus k. So the column space has rank n minus k. So that means any column vector should be in the span of these rows, right? So then you can ask the following. You choose a column vector, and you can ask what is the smallest number of column vectors you can span this one? And you can ask this for all column vectors, and you can try to find a number which guarantees using this number or less than that number, you cover everything. And this is the covering radius, actually. And this seems much easier to understand, at least to me. And this allows you to make a generalization, actually. Why do you consider only one-dimensional vector subspaces and you want to cover one-dimensional vector subspace of the column space? You can consider a two-dimensional vector subspace of the column space if n minus k is at least 2, and you may try to cover it using the columns. And it is called the second generalized covering radius. And similarly, you have other. And at the end of my slides, we have also some results for the generalized covering radius. Okay, so now I will jump into some classes of codes. Although I said in general it is difficult to compute the covering radius, but sometimes you can do it. And then you can publish papers, okay? And this is what we did for the MELAS code. So MELAS code were studied in various aspects in using also deep algebraic geometry by van der Gaar and van der Vlugt, but it seems they forgot or they didn't care about the covering radius, but we studied in the recent years. And we found the covering radius of the MELAS codes. It is the following. First of all, let me try to introduce how we define the MELAS code. So you start with a finite field Fq, then you look at extension Fq to the m for any integer m, and you consider the multiplicative group and let alpha be its generator. And you write all the non-zero elements in any order, right? I mean, in one order. So actually, if you choose a different generator, it will be just a permutation of the columns. But we don't care. We just fix one order. But once you go to the second row, of course, this order will be kept, and we just take the inverses of the elements of the corresponding column. So we consider in the extension field, we consider a 2 by n matrix. Actually, by abuse of notation, we call this also the parity check matrix over the field, since actually this is another typo. This should be Fq to the m here, since the entries are over Fq to the m. In order to go to Fq, you have to find just a one-to-one onto linear map from Fq to the m to Fq to the m. Then actually you get a parity check matrix. But if you do operations over extension field, whether a code word is inside or not, it doesn't change whether you use this parity check matrix or the other parity check matrix. But in any sense, once you understand the definition, then you can you may ask yourself to find the covering radius, and this is what we did. And we realized there were some partial results in the literature, and in 2022, we completed the covering radius of all MELAS codes. And you see, usually it is 2 or 3. And we will see most of our results will be covering radius 2 or 3. And actually, I will not go into details. We use a little bit from arithmetic of elliptic curves, and we use a lot of combinatorics, actually. And we have very nice pictures I like in our paper. But most of my talk will be based on Zetterberg cones, since I like there is a nice connection to fiber products of Kummer curves and Artin-Schreier curves, and that is what I want to stress in this talk. So Zetterberg code is defined similar to Melas code, but the difference is the following. So this is the reason of Q sub 0, I'm sorry. So we start with Fq sub 0, then our code will be over Fq sub 0. Then in the first half, we will only consider characteristic odd finite fields. And we take an arbitrary extension S, and the length of the code will be Q0 to the S plus 1. And then instead of taking all the elements of the multiplicative group of the extension field, we consider this somehow the polar case, and we consider the multiplicative subgroup of order Q plus 1 in the extension field Fq square, and we put all of them. Right? We even don't need the second row. And this is the parity check matrix. And this is still in the extension field. And if you look at carefully, I will not tell much about the minimum distance, but it is not difficult to see, it will have codimension 2s, right? So, but one thing, if you check carefully, this code, actually I should say, this code has minimum distance 2. Yeah, since 1 and minus 1 are there. So actually, we will use some part of the columns and actually half of the columns, and which half of the columns we will use will be depend on the parity of Q sub 0. But I will not go into details, but actually we show that the covering radius of this code is the same as the covering radius of the code after this operation, and it is easier to compute the covering radius of the Zetterberg code directly, and it will give the corresponding result immediately for the or twisted off Zetterberg code, and these are the codes which will give us infinite families of quasi-perfect families. So, in order to tell what we did, I have to introduce further notation and tools. First of all, in year 2023, we studied this problem, and we solved this problem in all cases except this strange condition. If Q sub 0 is not equivalent to the 2 to the L minus 1 for L, if it doesn't satisfy this assumption, we solve this problem here, and there are a lot of infinitely many odd characteristic finite fields which doesn't satisfy this problem, and we had I think 4 subcases to study, and we stopped at that point, since if we need to assume this thing, there are infinitely many cases, and for each case depending on L, for example the first case L is 3, we had to study 8 cases, then 16 cases, 32 cases. It is impossible to write infinitely many papers. So, but then we see that actually all the remaining cases simplifies, and this is what we do, what I explain now. Yeah. So therefore, this is for the remaining cases, we have this assumption, and we have a primitive 2th root of unity 1, and we still start with this multiplicative group, but especially, so in order to find the lower bound on the covering radius, we have to study much larger multiplicative subgroups, and this is the multiplicative subgroup we have to study. It is m times size m times q plus 1, and m is half of q minus 1 over 2, and this m we will see a lot in the next slides. I have to say, everything we started with the results of Dodinikov, which is for F2, and then for F3, Gashkov and Sidelnikov, and we used their ideas, actually, but very easily their ideas could not be generalized, and we had to generalize many further tools, but starting point were their excellent papers, actually. And so, after a lot of computations hidden, I do not explain here, so now we have a similar situation. First of all, the problem of finding the covering radius in this case, if the covering radius will be either 3 or 2, right? And the covering radius will be 3 if and only if everything in the big field Fq square here can be written as summation of as a span of 3 elements in this big multiplicative group. So this is always a problem from additive and multiplicative structures, as many interesting cases happens. So, and actually you don't have this problem in the Dodineco case, but then Gashko, and it is very difficult actually to do some arithmetic over Fq square and to conclude something over Fq. It is almost hopeless. But then Gashkov and Sidelnikov had an excellent idea. So instead of studying everything on Fq square, so we study only some very partial spread. And these are one-dimensional vector spaces, and these are Fq actually. So, and we have, instead of studying, so there are Q plus one-dimensional spaces to cover everything spread, but we study only 2 to the L many of them. And if we solve this covering problem only for each of these cases, it is over, right? This is one observation. And this says that, so these one-dimensional vector spaces are defined by this way and depending on the primitive 2 to the Lth root of unity. And in order to show this is most of the paper is about the covering radius is 3, not 2. That means we cannot cover by 2 elements, and this is the second definition. So this will be used for the upper bound, and it is for property Pi, and the lower bound will be used for property NPi. And actually, these are the results. So this is what I meant. If the property Pi holds for each these one-dimensional vector spaces, 2 to the L, then it will be, the covering radius will be atmos 3. I do not explain the details, but one can do some arithmetic and using similar methods from Gashkov and Sidelnikov and using exponential sum, Weyl sum, not as a Weyl sum, one can prove it, and we did it. Yeah, then the covering radius is atmos 3. But what about the lower bound? So first of all, so the second thing, we have to check whether the property NPi holds for at least one of these cases. So we cannot cover only with 2. And this is a nice part for me. And this NP, that it is not solvable, surprisingly becomes equivalent to this fiber product of Kumar extensions is solvable over the extension field, right? Over Fq to the S, Fq sub 0 to the S, right? And first of all, this is a very big Kumar extension. So we go through all quadratics in the base field. So it is a huge, it is a large genus, but we will see much larger genus in characteristic too. And these are the cases, this when you run through these 2 to the L even indices, and if you run through the odd indices, you have the same curve, but with covering in the right-hand side all quadratic non-residues. Right? So then this is obviously easy. Yeah? This is a nonsense problem if the extension degree is 2. So therefore, so we immediately get if S is even, the covering radius is 3. Yeah, but what happens if S is odd? Right? I don't know, and it seems it is very strange when S is odd. And for S is odd, what I know, we use Hasse-Weil inequality. If you go to a sufficiently large extension, you can always find a solution. And this is the degree. So S star is the, so we know that if you start with Q0, if length of the code is sufficiently large, the covering radius is always 3. But there is something in between finite interval. So the finite interval, let us define the finite interval in the beginning. This finite size of finite interval, we know what is the limit of this finite interval, but we don't know exactly what. So we studied by Magma some examples, and we don't know this finite interval, to be honest, for a given Q sub 0. It is, I think, a difficult problem. But using this finite interval for any Q sub 0, we find a lot of new quasi-perfect codes, right? Okay, so then what about characteristic 2? All of these are nonsense in characteristic 2. You don't have quadratic extension in characteristic 2. So, but you can define similarly the same zeta bar code in characteristic 2 using the same multiplicative group Q plus 1 over, so Q is Q sub 0 to the power S, and okay. So again, I will not go into details. But I have to give some definitions in order to present the fiber product, the horrible fiber product. You will see. So first of all, for any A in Q sub 0, we define this subset. So square root is a Frobenius automorphism in characteristic 2. So this is a F2 linear map, which is then actually it is very easy to define. It is a subspace of Fq sub 0, and if you run through that, and I have to consider all of them. When A is 0, it is everything. Otherwise, you consider actually all hyperplanes in Fq sub 0, right? So then you choose a basis. And once you choose a basis for U1, you obtain a basis for everything, and then you define some variables, and this is the fiber product. So for A is 0, you have elliptic curves. Actually, you have the fiber product, all of them. Then you have to consider the fiber product of the others. And you have to run through everything, like in odd characteristic. You have to cover everything. And once you do this, this is the result. I mean, but before going to result, in order to have an Hesse-Weil type bond, I have to find the genus of this curve, which is not very trivial. I had to introduce some further notation for just to be able to compute the genus. So the notation is the following. Just to compute the genus, I had to introduce an omega vector space. So this is the number of rows in the fiber product, and I have, so this capital M is the relevant F2 linear subspace. It is a very big vector space, and then I have to define some partial weights for each component depending on the partition, and I have a global weight. Once I define all of this, I can show that the genus of the curve is this sum. And this is, I have to sum through all subsets, the cardinalities of all these subsets, which are defined by the weight, global weight I just defined, right? So this comes from algebraic curve theory. Actually, Kani and Rosen, I should cite, actually, and also Arnaldo and Henning, using their techniques. This is what we get, but we have to compute it, right? And then using some, I have to give sometimes calculus courses in order to be able to compute this kind of identities, as not to forget. So I tried, and then I found using direct counting arguments, and after some careful, I tried to do it very carefully, and I checked. I think this is correct. I checked many special cases, and this is the huge genus right at the end. So in the calculation, we also use some combinatorial binomial identities, and this is the genus. And then Why? So just the first theorem is actually if this fiber product of Artin-Schreier extensions have a rational point, then the covering radius is 3 analogously. Otherwise, the covering radius is 2. So therefore, this is similarly what we did. So that as star be the smallest integer, I just plug in this genus, new genus in the Hasse-Weil, and then if our extension is sufficiently large, the covering radius is 3, otherwise the covering radius is 2, right? So, as I promised, let me now go to generalized covering radius, and I will go to another class of codes, which is probably more famous, BCH codes, and I will stick to binary field only. So, binary primitive double error correcting BCH code. So you can forget all I did. I will revisit the notions and definitions again, since it will be very easy. The real problem will start afterwards. So this is the parity check matrix. What you do is you take a primitive element in the extension field F2 to the M, and the first row is you write everything, yeah, all the elements of the multiplicative group. But in the second row, different from the Melas code, you take the cubes, right? Of course, you cannot take the square, right? It will not give you anything. So this is the BCH code double error correcting. We know the minimum distance is at least 5, and we know the parameters. So the problem is, what about the covering radius, and what about the second generalized covering radius of this code? Okay, so actually, what does covering radius mean is the following. You can forget everything. It means the following. So if I give you beta 1 and beta 2 in F2 to the M, can you always find a solution of this system of equations with 3 variables? That is what covering radius is. So actually, if you go to 2 variables, x1, x2, x1 cube, x2 cube, you cannot find for some beta 1 and beta 2, so the covering radius is 3, right? And this is a classical result, okay? So then what is second generalized covering radius? The second generalized covering radius is the following. So you want to put beta 1, beta 2, and beta 3, and beta 4. You want to cover everything using x1, x2, x3, maybe x4, x5, x6, right? Obviously, you can cover beta 1 and beta 2 with 3 columns, and you can cover the second syndrome using other 3 columns. So you need at most 6 columns. But the question is, can I use 1 column for both of the solutions so I can reduce to 5 columns? Right, that is the challenge. And actually, recently, this year, Yohananov and Moshe Schwarz obtained, yes, it is possible, always, except a very one case, right? So we tried to understand this, right? And here they want actually, we can extend, I think we can extend to any. I think upper bound is not a problem, but lower bound is in the Zetterberg code case is extremely difficult, and we could solve it when M is even completely. We could partially solve it when M is odd. And with my student, Iknur, we did for the triple. So we have 3 syndromes. And then if you use only 1 covering radius, you may solve it with 9 columns. If you use the results of Yohananov and Schwarz, you can do it 5 plus 3, 8. But we showed that you can do it with only 7, right? So we could put 2 columns and we could it on top of the others. So the proof for the upper bound is actually not very difficult. We use, as you may guess, we use this fiber product of elliptic curves. Okay, these are not elliptic curves, fiber product of Artin-Schreier extensions, and if you compute carefully, the resulting curve has genus 7, and we know there is a solution. Yeah, but for the lower bound, I will not go into details. It is difficult, and as in many cases, so you see the covering problem here. There are some cases that you don't, it is difficult to decide whether you can cover only with 6 columns or do you indeed need 7 columns, right? And this picture actually explains this situation. I didn't prepare all the details, but we could show that in the case even integers, we can show that this configuration is not a problem. We can indeed find 3 syndromes that we cannot cover only with 6 columns. But for the odd case, we couldn't. We say it is at least 6, or at least obviously it is not 5. So yes, I'm a bit early, probably. That is all I want to say.
Thank you very much. Questions for the speaker?
Thank you, Ferruh. So I have just a couple of questions about the Artin-Schreier tower that you showed at, I guess, slide 30.
The complicated one, you mean, right?
Yeah, the long one. Yep,
Yes.
yeah, that one. Go ahead.
Sorry. Yeah, I am going very fast and in the wrong direction. Yes,
okay, this one. So my question is, how difficult and which techniques you use in order to get the absolute reducibility of this curve? And secondly, I mean, clearly you have some bounds each time on the genus, no? Yeah. That you can just use instead of computing the exact genus. So I was wondering, what is the difference in this case between the trivial upper bound on the genus that you can get using some the fact that they are Artin-Schreiers and what you got exactly?
Yeah, I mean, actually, it is, you see all the poles are different, yeah, here.
There, yeah, but in the...
And these are linearly independent. Theta 1, theta 2, they are linearly independent. And one can show they indeed form a absolutely reducible curve.
Okay.
And for the genus, I studied in my PhD thesis a lot about fiber products of everything. I know I can compute the genus, and I computed.
Okay.
Yeah, that I didn't.
Okay.
Yeah.
Okay, thanks. Thank you.
All right.
More questions? Thank the speaker again.
So, all right. Let's go for the list of announcements for today. Just to remind you, today at the coffee break, you have another team of posters, presenters, but yesterday I have a list of people here who were presenting posters. Let me just call their names: Tiago Apridio, Lídia Silvia, Walter Silva, Carlos Marinho, Milena Maciel, Selma Araújo, Jaime Rodrigues, Arthur Fernandes, Abraham Vega. So I want to invite you to join me in a round of applause for these people. Please stand up if you are around. It was a fantastic presentation. So. And also, let me also remind you that today, this evening, we have the conference dinner, which was originally scheduled for 7:30 p.m., but then we have a small adjustment. The dinner will be at 8 p.m. And let me just to write down, the name of it's very...